This video is about activity, which is effective concentration, and has to do with ionic strength as well as other factors. You can see in the images that initially we have two beakers that have the same iron thiocyanate. When potassium nitrate is added to the beaker on the right, you can see that there's a color transition that indicates that there's more free iron and free thiocyanate in solution. This demonstration highlights the importance of ionic strength in consideration of the solubility product. It depends on the ionic strength, and that ionic strength is mu, and it's 1/2 times the sum of each species, the concentration of each species in solution times the charge of that species in solution squared. So, what does that all really mean? Well, the ionic strength is the total number of ions in solution. So if you had 0.1 molar sodium chloride solution, you would have a mu equal to 1/2 times 0.1 times 1 squared plus 0.1 times 1 minus 1 squared. So the squaring is what takes care of the charge, makes it all positive. So the mu equals 0.0. Ions in solution are surrounded by an ionic atmosphere. Increasing the ionic strength of the solution, or the charged species in the solution, increases the strength of the ionic atmosphere, which effectively decreases attractions between individual charged ions. As we saw in the example on the opening slide, adding an inert salt to solution and increasing the ionic strength can increase the solubility of sparingly soluble salts. Here's a graphical representation of that, where you have the reaction quotient on the y-axis and the concentration of the inert salt added on the x-axis. You can see that the concentration of the iron and thiocyanate anion in solution increases with increasing potassium nitrate. The result of increasing the ionic strength is that you can actually increase the solubility of a sparingly soluble salt. So you increase the ionic strength, you increase the solubility, and that's because there's a decrease in the attraction or repulsion between the anions and cations of the sparingly soluble salt, so more of it's likely to dissolve. And it also decreases the apparent concentration of the salt in. Activity is really the proper way to think about an ion in solution. And it has both the component of the concentration and also the activity coefficient, which accounts for, among other things, ion size and ionic strength of the solution. It essentially deals with non-ideal behavior of ions in solution. Alright, let's talk about the activity coefficient, which is basically the apparent concentration in solution. The activity coefficient is calculated using the extended Debye-Huckel equation, which is shown in the lower right-hand corner. So you can calculate the activity coefficient for a species using the extended Debye-Huckel equation, where you have the log of the activity coefficient equals negative 0.51 times the square of the charge times the square root of mu, which is the ionic strength, over 1 plus alpha, which is the size of the molecule, times the square root of mu over 305. And that's good at 25 degrees C for mu less than 0.1 molar. If you want to let's talk about trends in the activity coefficient. Then these trends are good for a mu of less than 0.1 molar solutions. So if you have an increase in mu of ionic strength, the activity coefficient goes down. So as mu goes to 0, the activity coefficient goes to 1. So another thing is that as charge increases, the activity coefficient becomes more important. So for a monovalent species, activity coefficient is less important, or is less impactful, than if you had, say, aluminum-3 in solution. Another thing is about size. As size decreases, activity coefficient becomes more important. So here's a couple of assumptions that we're going to use for this class. and so that is that activity coefficient is equal to 1 for all neutral molecules, and that the fugacity is equal to 1 for all gases. So the fugacity is just the activity coefficient for gases. It's called fugacity. Activity coefficients are assigned by convention. Non-ionic compounds that have no charge have an activity coefficient equal to 1. So the activity in solution is actually equivalent to the concentration. For solids, the activity coefficient will also be defined as 1. For gases, the activity is called fugacity, and the fugacity coefficient, which is equal to which is essentially the same thing as an activity coefficient, and is assumed to be equal to 1 for most gases under about 1 bar pressure. This is where gases behave ideally. Activity coefficients are particularly important for high ionic strength solutions above about 0.1 molar. When I said that when you measure pH, it's not exact, or the pH is not exactly equal to the negative log of the hydronium proton concentration, that's because a pH meter actually measures activity of the protons in solution. So the pH is actually equal to the negative log of the activity of the proton